We're going to derive in this video an equation known as the mirror equation. Now what I'm going to do in this video is not intended as an example or something that I expect you to be able to do yourself. I just want you to follow the argument. And I want to emphasize to you that the formulas in physics don't come out of nowhere. Okay, they come out of, in this case, basic geometry. Okay, and so I'm going to derive the mirror equation for you to help you see where it comes from. And then in the following video, we're going to do an example with it. But sit back, get a drink, and follow along. Okay. First thing I want to do is tell you what we've got here. What we have here is a convex mirror, and the object is far from the mirror. It's out beyond the point C. So this is case 1. Remember the 3 cases we did for the concave mirror? Did I say convex a moment ago? I meant to say concave. I don't know what I said, but I meant to say concave. The concave mirror has 3 different cases. This is simply 2 different looks at the same case. The case where the where the object is out beyond the radius of curvature, out beyond point C, when the object distance is greater than the radius of curvature. And what I've done in the first picture is pick out a single ray and traced it. And in the second picture, with the same physical setup, I've picked another ray and traced it. And I'm going to make a couple of quick geometric arguments, and we're going to come up with, poof, magically, the mirror equation using math. Okay, here's what you got to remember from geometry. Whenever you took it, 10th grade, whatever, I don't know. If 2 right triangles share a common angle other than the right angle, they are similar. So if I can find 2 angles that are right triangles, and if they both have, say, one of their angles is 23 degrees, those are similar triangles, which means they're proportional to each other. Okay, doesn't mean they're not identical, they're not necessarily the same size, but they're proportional to each other. One of them is just a bigger version than the other one. Okay, that's what similar means. And so what I've got here is, in the first case, I've got my object, like I said, out beyond point C. And I've labeled 2 new things here as well before we get into the details. H0 is the object height, HI is the image height. We'll talk about magnification, and I think in another video, and maybe the next video, we're going to say more about H0 and HI. Object height, say 6 centimeters, for example. Maybe the candle is 6 centimeters high. Image height, in this case, might be something like -3 centimeters. The negative means that it's upside down. A negative image height means that it's inverted, okay, relative to the object. Okay, so object height H0, image height HI. But HI is negative in this case because it's inverted. Therefore, if we look at this ray, okay, now if we look at this ray, this green ray is going to bounce off the middle of the mirror, and according to the law of reflection, when it reflects, the angle of reflection and the angle of incidence are going to be equal. So those 2 angles are both equal. Okay, so if the top theta is 15 degrees, the bottom theta will also be 15 degrees. That's just the law of reflection. There's our normal line right there. The principal axis is, in this case, our normal reference line. So those 2 angles are the same. So both these triangles, which triangles, you ask? The shaded ones. See, inside this long triangle here, it's all shaded, and in this shorter triangle here, it's all shaded. Those 2 are similar triangles because they're both right triangles, and they both share a common angle theta. So they are similar. Okay. And what that means is the ratio, say, of H0 to negative HI is the same as D0, which is the long side. So basically the ratios of your sides are equal. H0 is to HI as D0 is to DI. That's what similar means. the ratios are the same. And we put the negative sign in there because HI is itself negative. So the negative HI becomes positive. That's why the negative sign there. Again, similar triangles. Shaded triangle on top is similar to the smaller shaded triangle on the bottom, which means the ratio HI to negative HI, HO to negative HI is the same as D naught to DI. That's what you learn from that ray, that ratio. And actually I want to sort of star that because we're going to come back to this in the next video. Okay, we're going to come back to this equation. Sort of, clip and save, pigeonhole that. Okay, we'll come back to it. That's an important little equation that we'll come back to. Okay. And again, the negative sign is just because we define inverted image heights to be negative. So that makes H naught over HI overall positive because HI itself is a negative number. Okay, so that's what we learned from that ray. Same physical setup here. We're just looking at a different ray. Now we're looking at the ray that we called C before. Right? It's going to leave the candle, it's going to pass through C, and it's going to reflect back on itself and head on back out that way. That's what the C ray does. Now our two similar triangles is this one here and the smaller one there. You see those two? They both share the similar angle, which I'm now calling phi. Doesn't matter what we call it. Phi is a very common, we don't have to use it much, we'll use it some in the future. Is also a very common symbol for angles. So this triangle here is similar to that triangle there. And remember, where's my white? Where's my white? There it is. Here's our HO, object height, HI, image height. Again, negative. So that the ratio HO over negative HI is itself positive because HI is itself an intrinsically negative number. So negative times a negative on the bottom gives you a positive. HO is positive, so this is a positive ratio. So because these two, this gray triangle, this shaded triangle here, and this smaller shaded triangle there are both similar. They are similar triangles because they share that same angle phi. That means that the ratio of their sides is the same. So this ratio HO over negative HI is the same as this side of the big triangle, which is D naught minus R. If you look at the object distance and radius of curvature there, this distance is this distance minus that one. So D naught minus R goes there. That's the side of that triangle, right there. The similar side of the smaller triangle is this distance here, R, minus that distance, DI, R minus DI. So again, it's an argument from similar triangles. H naught is to negative HI, as this side, D naught minus R, is to that side, R minus DI. Sorry. Let me say it one more time to make sure I said it right. H naught to negative HI is the same as DO minus R, which is the side of the larger triangle, divided by R minus DI, which is the similar side of the smaller triangle. So these two are both true at the same time. So if those two are both true at the same time, they're both equal to H naught over negative HI, so the right-hand sides must be equal. So we can write D naught over DI is equal to D naught minus R divided by R minus DI. And we're going to rewrite this, do a little bit of algebra. So buckle up and follow me here. We're going to cross multiply. So that D naught times R minus DI equals DI times D naught minus R. Just cross multiply. Totally legal move. Now I'm going to distribute. D naught R minus di do is equal to di do minus di r. Okay. Now I'm going to add di do to both sides. So plus di do plus di do. And we're going to get on the left-hand side d naught r equals 2 di do minus di r. Okay, I just added di do to both sides. Now I'm going to add dir to both sides to move it over here. And we're going to get d naught r plus dir equals 2 di do. Okay. Got to rest for a second. Take a deep breath. Chill. Grab some coffee. Now we're going to divide all the terms by di do. Why? Because we can. And we're going to get some nice cancellations. Let's see what we get here. The first term, we're going to cancel our do's. Second term, we're going to cancel our di's. And the term on the right, we're going to cancel our di's and our do's. So we've got r over di plus r over do equals 2. Now please notice, remember from before, for a concave mirror, f is 1/2 r. So r is 2f. So we can now replace our r's with 2f over di plus 2f over do equals 2. And we can, all of our 2's cancel. They don't become 0, they just become 1, right? We can divide both sides by 2. And then if we multiply both sides by 1 over f, what we'll end up getting is this. We end up getting 1 over do plus 1 over di equals 1 over f. And that is the mirror equation. Okay, that's it. That relates object distance, image distance, and focal length. Remember, the focal length basically tells you how curved the mirror is, how tightly curved it is. The flatter the mirror is, the larger the focal length. The more it's rounded like this, the smaller the focal length. Okay, so it connects the geometry of the mirror through f with the object and image distances. All right, so that is the starting point for the next video, where we're going to work a couple of examples using that. And also, we're going to bring in the idea of magnification as we work these examples. All right, see you then.